So Dominic Benford is the program scientist for the Nancy Grace Roman Space Telescope, um, and uh, and with a major survey for the near infrared to understand better dark energy and the distribution of dark matter, and the occurrence of planets around stars, exoplanets, and even enable direct imaging of planetary systems. Dr. Benford is the Deputy Chief Technologist for Astrophysics with responsibility for Strategic Astrophysics Technology, SAT, the Roman Technology Fellowship, RTF, and other technology-focused programs. He was also the acting lead for the Laboratory for Astrophysics, and previously his roles at NASA HQ included being the program lead for APRA portfolio, including funding early-stage technologies and suborbital class projects, and roles on Euclid and the Origin Space Telescope. So with that introduction, Dr. Benford, I would love to switch over to you.
Well, thank you all for having me to speak with you tonight. I'm excited to be here because this is the big year for the Nancy Grace Roman Space Telescope, which has been under construction for several years now and will launch later this year, sometime in the fall. So I'd like to spend a bit of time talking a bit about what the Nancy Grace Roman Space Telescope is, what it's for, how we built it, and hopefully we'll have some time for a little bit of interaction and discussion. I love doing these things in person where you can ask me questions, you can interrupt in real time. It's a little harder to do online, and I don't know whether your standard is to try to ask questions all at the end, but I'm certainly happy to stick around and address any other lingering concerns you have that aren't covered in what I've prepared. So I know that you're a club of people who probably know vastly more about astronomy than I do, but I always like to start a little bit with some of the basic reasons of why we're doing the things we're doing, specifically why we're doing the Roman Space Telescope, but more generally, why we want to invest in curiosity-driven scientific research like astronomy is. See if I can advance the slides. So the fundamental questions that we are trying to address with the Roman Space Telescope, there are two of them. How did the universe that we see today around us come to be the way it is? And those are largely the aspects of the universe that have been pushed forward by dark matter and dark energy in various ways combined. The second big question are whether planetary systems like our own are common, rare, or possibly even unique. Because at the moment, we have only one example of a solar system like ours with a large number of fairly widely spaced planets. We don't know if there are others out there. And one of the great things about astronomy is that we all come built in with these wonderful tools that allow us to understand something about what we see in space. And the human eye is a great tool. All of you probably use yours regularly with telescopes to aid them. And we've been trying to build better instruments and better instruments throughout human history, really, so that we can do better with these eyes to see more and more of what's in space. Because frankly, the human eye is very, very good, and but only good enough to see at some distance, really, with any reasonable acuity. So you can easily see this one object in the night sky, and well, most of the time. And it's something that we are all very, very familiar with and has been around since antiquity. The problem with viewing this object is that one of the limitations of our eye is timescale. It's made to look at things that move at human speeds, things that change on timescales of seconds, possibly minutes, not things that change on timescales of days. Matt, I see you're getting in front of the camera again. Are things still okay?
Sorry, I'm trying to fix the audio a little bit.
Okay. Is it still too quiet? Should I just try to talk louder?
You're okay. Yep. Yeah, let's keep going. Let's keep going.
Okay.
Yeah. Okay, I'll get out of the way.
Yes.
Yeah.
So one aspect of what the Roman Space Telescope and others can help us do is to change the time scale at which we observe objects. Now we'll try our first animation. Hopefully this will come through online. If you could see the way the moon moves over its 28-day cycle in quasi-real time, speeding it up to a way that is reflective of what a human can easily perceive, the moon moves in a much more complicated way than most people are aware of. And this is true about many astronomical objects, that they move or they change in brightness all the time. And it is only through the use of advanced tools that we can sense these things. And one of the great things about astronomy is that these tools are sometimes fundamental. In antiquity, the movement of the moon and the planets and the sun across the sky in the seasons, across all of the constellations, were the way that people could define a calendar, and the calendar could define the seasons of the year and help you figure out how to plant crops and things like that, so that astronomy was tied fundamentally to food production. As in the case of Enhedu Anna, often claimed to be the first astronomer who helped to figure out things like this, including that Venus was both the little star that you saw in the dawn and the little star you saw in the evening. Now, later, people began to think that since astronomy had all that kind of power, that you could use it to predict the future, such as with an appearance of Halley's Comet on the Bayeux Tapestry that was used to predict or maybe post-dict the Norman invasion of then Saxon England. And now we understand it in a much more scientific way, that astronomy is the tool that we use to understand the universe around us and fundamentally how that brought all of us to be where we are right now. And to do this, we've built a wide variety of tools, not just telescopes, but robotic instruments that have gone out and explored now all of the planets in our solar system, plus a number of minor bodies. So we've really been extending humanity's reach through all these great tools. And Roman is just the next one in that kind of sequence. Of course, we get to discover so much more by actually going to various places. And I just wanted to put this up because it is so pretty to see all those planets there. Now, the purpose of Roman is partially to see far, far away. We have a lot of ground-based telescopes that are very useful for seeing things in our own solar system quite easily, and reasonably nearby galaxies and things within our own galaxy. These are all, relatively speaking, very, very close. Now, as you move away from the Earth, and it's going to be a little bit slow, there's very little around us in most of space, except for, of course, all these satellites that we've put in orbit, mostly not for astronomy purposes, mostly for things like communications. And sadly, for a lot of people in the ground-based astronomy community, including perhaps many of you, there's now a lot of light pollution from many of these. But space is very, very big, and most of space is very, very dark. And as we pull out, I'm sorry, I should have sped this movie up a little bit more. We've managed to send a number of telescopes out to roughly this kind of distance. The Spitzer Space Telescope, the James Webb Space Telescope, and the Kepler Space Telescope have all been in heliocentric orbits. Now, they don't actually get much more of a vantage point, but they do allow us to make some measurements from places other than the Earth, which is beneficial in ways that I can describe later. But then everything that we learn about the universe out beyond our solar system is all done by remote sensing, by building ever larger telescopes to enable us to see all of these distant objects remotely. It's a little problematic because so many of these things are so far away that we can't resolve them easily. We can't measure their size, their shape. Almost all of the stars are pure points of light. And for most ground-based telescopes, most galaxies are basically pure points of light. And we haven't even pulled away to the point where you can begin to see the galaxies because we're still in our own Milky Way galaxy here. And that little island universe, as it drifts away, just becomes one of many, many billions as far as the eye can see. And these are the galaxies that we want to be studying in great detail with the Nancy Grace Roman Space Telescope. It's determining the large-scale structure of the universe out to about as far away as we can see. Now you see there's an awful lot of blank space and an awful lot of relatively empty space, which we're going to fill in. And the information contained within that map is ultimately what will help us understand dark matter and dark energy. And that's the edge of the observable universe. So back to the human eye and our tools. Our human eye is effectively very, very small compared to the size of a telescope. Any of the telescopes that you all have and get to use at your dark sky sites are typically tens to hundreds of times larger. And perhaps the most famous one that we've built and put into space is, of course, the Hubble Space Telescope, where its mirror is a 2.4-meter diameter. It's roughly 8-foot diameter, coated glass mirror that reflects all that wonderful light into a set of instruments. And it has been, by some measures, the most scientifically productive piece of equipment that humanity has ever built. And it has been superseded in some ways by the James Webb Space Telescope, which launched quite a while ago now, but it's still fairly recent, about 5 years ago. And you can see it has this beautiful 6.5-meter mirror. So it's about not quite 3 times the size of Hubble in diameter, and beautiful gold-coated beryllium to optimize its reflectivity in mid-infrared light. It's a beautiful thing, and there's a little inset of me with it at the Goddard Space Flight Center while it was under optical alignment. And I showed you some pictures of the solar system objects, the major planets, and here are just the outer 4 gas giant planets that we have, seen by Hubble in the visible. And you can see that they all are beautiful and familiar and colorful. And the most prominent feature you might see around Saturn, of course, are its rings. And when you look in the infrared with the James Webb Space Telescope, you of course see that all of those planets have pretty prominent rings. You could argue about whether Jupiter's are prominent or not, but the other ones, certainly Uranus and Neptune, have very noticeable rings. And it's great that you could have access to this kind of information with a telescope that you've put into space that you couldn't have acquired easily from a telescope on the ground. Now, that's useful for measuring things in our own solar system. It's even more useful for measuring things in distant galaxies, where the set of fairly similar looking galaxies all observed with the Hubble Space Telescope, they are, roughly speaking, spirals, and you can see they have dust lanes and regions of greater or lesser stellar density for these spiral density waves. And if you look at them in the infrared with the James Webb Space Telescope, you can see that spiral structure. It's still there in the first one, less obvious in the second one. It's a very different sort of structure in the third one. And then again, a rather different, more like barred structure you see in the fourth one. Your eye now picks out very different details when you see these different wavelengths of light because they're tracing physically different material. Instead of stars, you see a lot more of the gas and dust between the stars. So this is my argument for why the infrared is a powerful additional diagnostic. But there are also things that you can learn about it just looking at regions in our own galaxy, such as the famous pillars of creation, the Eagle Nebula, seen here with a Hubble image, and seen here with a James Webb Space Telescope image. You can start to see through these clouds of gas and dust and see where the stars are actually being born in these young stellar regions. They may not be too obvious to the untrained eye, but they're the exceptionally dark red spots that you see particularly near the tips of these fingers. Those are the most deeply embedded parts that have the young stars embedded within them. Shift wavelengths a little bit to bring up the contrast somewhat. Now, there's a common feature of these telescopes, both the Hubble and the Webb. They are essentially telephoto lenses. They're designed to see things very far away and study individual objects, such as when somebody with a telephoto lens might be taking a picture of a bird or a sports figure, someone far away from the photographer. So when we did this, looking at the most distant parts of the universe with the Hubble Space Telescope, the original Hubble Deep Field, which was imaged back in the 90s and has been superseded with several repeat observations of this, is a big patch of galaxies, roughly 10,000 galaxies in one chunk of sky, and here it is. But you have to zoom in so very far that by the time you've imaged this patch of sky, you're looking at a very, very tiny fraction of what the universe has to offer. Now, Hubble has done a spectacular job of helping us understand these galaxies, but it's such a small patch. If you compare that to the size of the full moon, it's much, much smaller. And as you all know, the full moon is a very small fraction of the overall sky. In fact, about less than 100,000th of that. And the Hubble Deep Field is a tiny fraction of only of order of percent of even that. And that's very limiting. So when you're looking out at the universe, some of the time when you see things, you'll just see little blobs. Now, this might be something that looks like a galaxy or a globule or something, but it's actually, I believe, a bird. but you couldn't tell this because it's a single little image very far away. And this is essentially what you do with things like Hubble and Webb. You look at individual objects far away and do your best to understand them. But what you'd like is to pull back a little bit and build a bigger camera. So let's say that we could build one that was 100 times larger. So say a 10 by 10 grid of these. And then you can see the bird flying against the sky with some clouds in the blue. And that gives you a much, much better picture of what you're seeing. Now, if you also decided to make that camera much more agile so that it could image more quickly, you could say move that single field over and take a picture, and then move over again and take another picture, and do this faster and faster and faster until eventually you could build up a complete picture where that bird is still there, but now you have an image that is approximately 1,000 times larger than the original image, which was this little inset that I've got right there. Hopefully you can see it in the upper left-hand corner. I don't have your magic laser pointer, so I'll have to just describe where it is. And you probably recognize what we're looking at here. And of course, the Houston skyline. Now imagine that you're viewing the tiny little piece of space like around the Eagle Nebula. And you can imagine what it's like viewing that from the ground, particularly. The ground, of course, has all this lovely atmosphere that we so enjoy in the way, which blurs things. So you don't get as sharp a view as the Hubble Space Telescope. But now imagine if you could build something that had that same wide field of view that you get on a ground-based telescope, but with the sharpness of a space telescope. That's what we've built Roman to do. So we have a camera that has roughly 100 times the field of view of Hubble. And we've made it very agile so that we can take pictures repeatedly and mosaic them together. And this is kind of indicated in the illustration here. We can also then roll the telescope so that we can fill in all the gaps in our images quite easily and effectively make solid mosaics with approximately 1,000 times the speed of the Hubble Space Telescope. So that is a rendering of the Nancy Grace Roman Space Telescope in space. You'll notice that it actually looks rather like Hubble. It's approximately the same size, a 2.4 meter mirror, somewhat shorter focal length to have a wider field of view. And here's our nice little pretty picture of it. We had originally designed this with a commitment that it would be launched by May of 2027. We're currently on track to launch it later this year, something like 6 months ahead of schedule. The reason that we are building Roman comes in part from a sequence of recommendations that the National Academy of Sciences issues. They do this every 10 years. They advise NASA and other government agencies about what the highest priority projects should be to maximize discoveries and American leadership in space. The 1972 Decadal Survey is what recommended Hubble. In 1982, it recommended Chandra. About 10 years after that, Spitzer, and then Webb, and now Roman. So Roman was recommended in 2010, and we spent several years studying it before we began building it in earnest. But it will be, from its date of recommendation to launch, something like 16 years, which is faster than most of these. Now, what the Decadal Survey told us to do is to build a capable observatory with several key features. First, that it would be able to provide wide field surveys, survey the universe far faster than has been possible with any other space-based telescopes like it before. The second is to map the evolution of the universe, how it expanded and how the structures in it formed over all of cosmic time. The third is to conduct a survey that would answer fundamental questions about exoplanet demographics, that is to say, what planetary systems are like around other stars, not just individual planets, but planetary systems around other stars. And finally, to advance technologies for being able to see new worlds, what we call direct imaging, where you block the light of a star so that you could see the reflected light of a planet orbiting that star. So I've already mentioned that the camera on Roman is much larger than Hubble's. In the infrared, it's actually more like 200 times the size of Hubble. In the visible, it's more like 100 times. Now, Hubble has already given us a lot of information about both the expansion of the universe and the growth of structures within the universe. And it is from these that we know so much now about dark energy, which was in fact discovered by measuring supernovae using the Hubble Space Telescope, and the growth of structure that hints at dark matter, which we use Hubble for quite a lot to image particularly strongly lensed regions full of dark matter that we cannot see. Now, for most of human history, we had a lot of information about our own planetary system, but other planetary systems that might have many planets that are close to our star, or hot and large, like these Jupiters that are right next to their stars. We don't have anything like that. Or planets that are tidally locked to their stars, or planets that are in between the size of the Earth and the size of something like Neptune, but these middleweight sort of stars, or middleweight planets. All of these other planets that we have seen, we can't fit them very easily into the context of planetary systems because we don't have good examples of these. And we want to answer that question I phrased earlier about whether our solar system is common, rare, or unique in having its configuration of planets. So, Roman. How does Roman do all of this? Now, I'm going to talk a little bit about the construction. We've built this with two instruments. One of them on the lower left is a coronagraph. The one on the upper right is a wide field camera. And a wide field telescope, which you'll see coming in the upper left, and a spacecraft bus, which is all the components you'll see in the lower right. I'm just putting all of these up there to indicate that we've spent a lot of time building a lot of hardware. All of these individual portions of Roman were completed and delivered at some point in late 2024. We then underwent the fairly big job of installing all these pieces together at NASA's Goddard Space Flight Center, just outside of Washington, D.C. You can see pieces of it coming together there. All of this happened a little over a year ago and was completed by the end of December of 2024. Here's a little video of the two major pieces. The core of the observatory is right in front of you with a telescope that you could see pointing upward. The camera is the big instrument to the left of that, and the coronagraph to the right of that, spacecraft bus underneath. There's an outer barrel, which is the larger structure with its solar panels you can see in the background to the left of the main observatory. And then, after having taken months and months to test it in a thermal vacuum chamber, we bolted these two pieces together very quickly in one day. Now, they weren't, this is of course sped up, they weren't moving quite like ants, but we integrated all of this actually only a few months ago. And so now the observatory is in fact complete. All the pieces are together. It is undergoing its final stages of testing now, which include things like vibration testing for launch loads, acoustic testing, the acoustics of launch being, of course, very loud and dynamic environment, and deployment tests. You can see some of that going on there as they were unfolding the solar arrays, which have to be done automatically in space. So these pictures were taken only a matter of some number of weeks to months ago, and you can see Roman in all of her glory there. It's quite a large telescope, about the same size as Hubble. Here's some hero shots of the crew that helped assemble all of that. So that's the instrument we have. Now, how do we actually use this to do the science that I've spoken about? So Roman is a survey telescope. It's not a pointed observatory, the way, say, Hubble and Webb are, where you pick individual objects and you study them in detail. Rather, Roman is designed to map the heavens in ways that we were unable to do with these other instruments, and to pick out, instead of small numbers of objects, vast numbers of objects, to study them in a scientific and statistical way. We will conduct several different surveys, all interleaved with each other. One of them, perhaps the best known, we call the High Latitude Wide Area Survey. Of the first 5 years of Roman's operations, we will take about 520 days spread across that time with our wide field camera to map a little over 5,000 square degrees of the sky, with exposure times, depending upon our depth, in a sort of a wedding cake fashion, ranging from about 10 minutes to about 2.5 hours. The second survey is our high latitude time domain survey. So that's looking at high galactic latitude, so away from the plane of the galaxy into the deepest, darkest skies. This is a smaller area, about 90 times the full moon, so just a few tens of square degrees. We'll spend about 180 days spread across a few years, but we'll be mapping it over and over again. A cadence of about 30 hours of observation every 5 days over this 18 square degree region. We'll be doing that because we'll be looking at the things that change, notably supernovae or variable stars or other transient events. We're also going to map some in our own galaxy. The Galactic Bulge Time Domain Survey is looking right towards the center of our galaxy, well, slightly off, typically, off the exact galactic center, towards the bulge where the greatest density of stars is found. This survey will take about 438 days, it's fairly precise, in 6 individual sets of observations that last about 2 months near the beginning of our observing time and near the end of the 5-year prime mission period. We will observe the entire area, which is a few square degrees, every 12 minutes, taking a deep exposure, looking for the very subtle and fairly quick changes in the brightness of those stars due to the presence of planets around them. We're also going to do a wider survey of the galactic plane as a whole. This is quite a large survey, and in this case, it covers of order 1,000 square degrees. It's very wide field, covering the huge amount of the galaxy in infrared bands where it is hard to see in the visible because there's so much dust extinction. We're going to do all of this in only about a month of time because Roman is so very fast at looking across so much sky. To give you an example of just that last one, here's the Carina Nebula pulling out. That was a map of that object and then a much wider field map made with the Hubble Space Telescope. Significant amount of time that put into generating this image. And when we pull out a single Roman image is larger than that entirety. A larger field that will be observed multiple times is large enough to cover an entire gas cloud like this. But then the full image region that I described earlier of 1,000-ish square degrees is a significant fraction of the plane of our galaxy and a significant fraction of the number of objects within it. So putting some numbers on what we will see with Roman, our estimates based on fairly well-known understandings of the frequency of events like this in the universe is that we will see tens of thousands, maybe close to 100,000 supernovae, thousands of planets that we discover by microlensing, 100,000 or so that we'll discover by transits, and with the same surveys, hundreds of new black holes, hundreds of forming planetary systems, and then in the major surveys, up to perhaps 1 billion galaxies and 100 billion stars in our own galaxy. So I'll talk a little bit about some of these things, what it means to be looking at galaxies by the millions. Now, this is an image you could probably tell from the James Webb Space Telescope where you could see thousands and thousands of galaxies. But we're going to be able to do this over much, much wider fields of view. And the information that we get is contained partially in the shapes and colors of all of these galaxies. And this has to do with how far away they are and how much the dark matter between us and those galaxies has distorted their image, and how much the gravity of all the matter has pulled the galaxies together to form clumps and clusters. You can see we're zooming in on a cluster right now. And how much dark energy has pushed these apart, creating voids between these clusters. This is the kind of image quality that we expect with the Roman Space Telescope. Obviously simulated images, because we haven't launched it yet, but we have pretty sophisticated simulations. Now we're also, as I'd said, going to be doing time domain surveys where we look at the same patch of sky over and over again. And this is a simulated movie where we've accentuated the brightness of many of these transient events, mostly supernovae that you see going off in all of these galaxies. All those little flickers are the vast number of supernovae that we see in the millions of galaxies that we will be imaging. This is what it looks like zoomed in. So you can see these little dots, individual stars exploding in galaxies far, far away. So it's a simulation, but we'll take data that will enable you to do this for real. So since you can measure galaxies by the billions, you can also measure stars by the billions. Perhaps a good example of this would be looking at stars in nearby galaxies, such as Andromeda. This is a famous image of the center of the Andromeda galaxy, the nearest neighbor. It was about 450 images with Hubble, only 2 images with Roman. And because we know what it looks like with Hubble, we'll know what it looks like with Roman. It'll look something like this, where these are stars in individual stars in a nearby galaxy mapped with exquisite precision. We'll also be looking towards the center of our galaxy, as I mentioned, and measuring the stars there. Now, the center of our galaxy is very rich of stars. This is a simulation based on the known stellar counts that we have of something less than 1% of the image that we will be taking with the Roman Space Telescope. If I tried to make an image like this of the full scale of Roman and shrunk it to the point where you could see it on this screen, you wouldn't even be able to see dark space between all the stars. It'd just be stars everywhere. We're going to use this to discover planets by the thousands, perhaps even to the hundreds of thousands. We already do know about 6,000 exoplanets. These are planets around other stars detected principally with telescopes like Kepler and TESS. And we have seen planets unlike any that we've known, particularly these close systems where all of the planets around a star might be closer than Mercury is around our own sun, and the famous mini Neptunes, these planets that are not as large as Neptune, but much bigger than the Earth. Some people call them super Earths. People have called them Neptines. We would like to know what these are because these turn out to be the most common form of planet that seems to be produced by nature, and yet we don't have any of them in our own solar system, and we don't know why. Perhaps by studying enough different solar systems, we'll be able to get a clue as to what it is that causes planets of that size to be the most frequent. So a little artist rendition of the system TRAPPIST-1 that has 7 planets, all closer than Mercury. This artist rendition shows the very reddish star, and then you can see 2 of the planets that are interior to the one that the artist has chosen to render here. And you can see that they are disks. They are clearly partially illuminated by the sun from their angle. And what I find so evocative about the idea of a planet like this is thinking that if intelligent beings were to come to fruition on a surface of a planet like this, that they would understand the heliocentric model of the solar system in antiquity because they could see it in their night sky or in their day sky. They could see all the planets as planets. And if there were other civilizations on those other planets that had, for instance, cities and cities with lights, you could see them from the other planets. You could see the lights and know that there was intelligent life elsewhere if it were there. Now, I'm often asked whether we have yet found, out of all those 6,000 and more planets, any other planets like our own. And the answer is we really haven't yet. We've gotten close, but to find something that is very much like the Earth, the same kind of size, the same kind of distance from its star that you can have things like liquid water on its surface, we don't really have a good handle on that yet. That's because most of the planets we've been discovered so far have been found by the transit method, which is where when you see a planet passing in front of its host star, there's a slight dip in the light from that star. We measure that dip, and that tells you the size of the planet. And when you see it coming around again, that tells you something about the orbit of that planet. And of course, you're more likely to find things that are larger planets that are closer to the star because they block more of the starlight, and they'll come around more and more often, so you can see those repeat dips. Roman is using a completely different technique called microlensing, where when a star passes in front of a background star, the gravity of that foreground star lenses the background star and produces more light that we would receive here on Earth. And similarly, if there's a planet around that foreground star, it also lenses the background star's light. And the great thing about this is that the signal is very large. Rather than blocking a tiny fraction of a percent of the star's light, it can amplify it, even doubling the amount of light that you get from the star for a very short period of time. So if you, and I apologize, I have to put one graph up to make this a science talk. If you were to plot all of the known planets, this was a couple of years ago, as individual points on this graph, where the y-axis is the size of that planet, and the x-axis, the horizontal axis, is how far away it is from the host star, those are all those little clouds of points in blue and gray. And just to give you an idea of where our solar system is, I put little pictures of each of our solar system planets there. And you can see at a unit of 1 distance from the host star and 1 size of planet is a picture of the Earth. Venus is the yellow one that's just slightly interior. Jupiter is a really big one that's further out and much, much larger. And then you can look at all of these exoplanets we've discovered. And they don't look anything like the planets that we have in our own solar system. That's largely because the transit technique that has been used to find them selects only things in that upper left region with the blue sort of bounding lines. We can predict very well what Roman is going to see because we have some idea about what the formation of planets should be like. We don't really know it because we are setting out to measure this. But with our best models, Roman will produce a survey that looks something like this. And all those points are possible places where we will find planets. And you can see that Roman has the ability to find all of the planets in our solar system, except for Mercury, because it's a little bit too close in. But it has enough sensitivity right there in the region around the bottom of that curve, where you could see an exomoon like the size of Ganymede around an exo-Jupiter. So maybe we'll actually be able to measure not just exoplanetary systems, but say something about moons in exoplanetary systems. Now we're doing all of this using time domain astronomy. That's the field of study of the things that go flash in the night. So we have this great camera to take wide field of view images like I've been describing. This one just illustrates how wide a 2000 square degree field is, and we're doing more than that, compared to the Hubble deep field. And the Hubble's deepest field is the cosmos field, which is the little white box that you see sort of to the right of the giant blue region. And when we have this tool with all of these new measurements, we're going to be able to find out things about new physics that we don't know yet. So we'd like to say we're expecting the unexpected. And that's partially because we are making all of this data fully available to the worldwide astronomical community with no proprietary access period. Everything, as soon as we process it, it goes into the archive right away and is freely accessible. Hubble has been operating for more than 3 decades, and it hasn't even quite gotten to the 200 terabyte level. Now, 200 terabytes is a lot. You probably have only a 1 terabyte drive in your laptops these days, so it's still a few hundred of those. Roman, in its first 5 years, will generate an archive of about 20,000 terabytes or 20 petabytes, a vast amount of data compared to what has been collected in the past. And of course, all of it will be freely available. And there was some discussion earlier today about the data science aspect of things. One of the aspects of what will happen with Roman that will be different is that even though the data are publicly available, we don't expect you to download it because we don't expect that you have a petabyte drive on your laptop. Instead, the data will all live in the cloud. And if you want to process the data or analyze the data in special ways, you would have to go to the cloud and access it there. So the processing will all be done online somewhere in a cloud service environment and to be abstracted away from you so that you don't have to store all of this and use your own compute power because it's not practical for everybody to do this. Now we're doing this we're building Roman to answer a number of really major questions. But we've built something with such great capability, and we're making so much data available to everybody that we expect that Roman will be used by most astronomers for most of their projects. It should be that capable, and we want it to be that capable. So this gives you an idea of some of the things that Roman is able to do, not necessarily why we designed it, but what we built will be able to do. Now, I would be remiss if I didn't mention a little bit what we're doing to point towards the future, because even though this is a great observatory, it's named in honor of Nancy Grace Roman, who was NASA's first chief of astronomy. She was hired when the agency was new and given the task to make space telescopes possible. And so she was the person who oversaw the first telescopes that we, humanity, ever launched into space for studying the distant universe. And one of the things that she should be well known for, and perhaps is not well enough known for, is that back in around 1959, before we'd ever put telescopes in space, she'd written a little paper that said, if you could put a telescope in space, which he thought would probably be on the moon, but somewhere in space, and you could come up with a sufficiently capable way of blocking the light from a star, you might be able to detect the light from a planet around that star. And so we carry an instrument on the Roman Space Telescope to do just that. It's our coronagraph. Now, this turns out to be very, very difficult because stars are very bright. And when you look at a distant planet that's, relatively speaking, very close to that star, it is completely lost in the glare of the star because it's so much fainter until you can block the light of the star and then see that faint light reflected from the planet. Now, this is difficult, but compelling, because if you can take the light and spread it out into a spectrum and measure the various absorption dips in its atmosphere, it'll tell you something about the chemical constituency of the atmosphere, presence of things, molecules like water and oxygen and methane and carbon dioxide, which together could signal the presence of life. That's a great goal. Now, Roman is not going to be able to do that. That is still beyond our technical capabilities. But what we can do is suppress starlight far better than has ever been done before. The best that can be done on a ground-based telescope is, as you can see on the left here, to block the light of a star at a ratio of about 100,000 to 1. Now, what you're looking at is an image of a star, which is in the middle, that has been almost perfectly suppressed, except all that noise that you see, the sort of blue and yellow scudge in the middle, is the residual unsuppressed starlight, and the planet is that little bit of light that is the blue dot just to the left. With Roman, we have built a coronagraph which we have measured on the ground, not yet in space, but we believe that its performance in space will be able to do the same kind of job, but about 100 million to 1 instead of 100,000 to 1. So measuring the fainter sources around those stars. We're pushing the envelope of what is possible by about 3 orders of magnitude. Now, 100 million to 1 may sound like a lot, but if you look at an exo-Jupiter, a Jupiter around another star, that is roughly where the brightness of an exo-Jupiter would be. To look at an exo-Earth, you probably need to get to be something like 10 billion to 1, so almost a factor of 100 better than this still, because Earth is a much smaller planet and much closer in. We are beginning to work on a telescope to do just this, which we've named the Habitable Worlds Observatory, because its key goal will be to try to find evidence of the habitability of planets around other stars. As a simulation of what you should be able to see, if you could suppress the light of our own star, looking at it from a distance, you should be able to see Venus and Earth and Jupiter and Saturn and see that they are different planets, in part because they would have different colors. And in a beautiful and perhaps somewhat optimistic movie, you can imagine being able to watch a system like that over the course of years and see the planets moving and measure a little bit about their chemical constituency and understand in more detail what kinds of planets these each are. So that is the goal, eventually, to be able to take that light and spread it out into a spectrum and analyze it and look to see for the signatures of things like oxygen, ozone, and water, which together, especially with things like methane, might tell us whether there is actual life, not just habitability, but actual life. And it's important to remember that we have to be broad about what we think life looks like. If you looked at the Earth across its roughly 5 billion years of life, it does not have, well, 5 billion years of the planet. It did not have life all that time, but it had life for most of it. It hasn't always looked like it does now, this beautiful blue-green dot. There was certainly an earlier era in the Proterozoic Earth when it had some of the same chemistry, but not exactly the same chemistry. So you can see that the spectrum was significantly different in the amount of things like ozone that it had. And then if you look even further back into history, into the Archean Earth, it's even more different. We used to have an atmosphere that had significantly more carbon dioxide and methane and significantly less oxygen. And life did form in this environment. We have to look for life in all of its possible forms and maybe ones that we haven't thought of yet. That's the field of astrobiology. Now, this is not what Roman will do, but it is part of what Roman is intended to support because we want to be able to demonstrate that the coronagraph is able to do what it has to do with a telescope like Roman's. When you put it on a larger and better telescope, we will be able to use that kind of instrument in order to make these measurements. And as the National Academy said, if we do discover the signature of life in another planetary system, it'll change our place in the universe in a way not seen since the days of Copernicus, once we really know what's out there. So I've tried to give a little bit of a flavor of a continuum of events from the recent launch of the James Webb Space Telescope, the very near future launch of the Nancy Grace Roman Space Telescope, and the context of supporting our path towards the Habitable Worlds Observatory, all coming up in the near future for Roman and in the next few decades in the case of habitable worlds. So coming back to the original questions that we were asking, how did the universe that we see today come to be? And are planetary systems like ours common, rare, or unique? These are questions that people have been wondering for as long as we've known to ask them. Certainly, the question about the universe is something that is fundamental to many religions because they try to explain this. We are on the brink of being able to launch a telescope that will address these questions. The Nancy Grace Roman Space Telescope should launch later this year. It'll go through commissioning, and by January, just a little under a year from now, it'll be pouring data back to us as rapidly as we can analyze it, a little over a terabyte per day. And these questions are things that we will address and answer. So when we give presentations like this a few years from now, there'll be a slide like this with the question and a slide like this with the answer to that question. This is all within our reach in the very near future. I'd just like to end with a Carl Sagan quote because he was very good at this sort of evocative ideas. Once we lose our fear, being so tiny and small, we find ourselves on the threshold of a vast and awesome universe, which we are going to be exploring anew with the Roman Space Telescope. I'd like to stop there and see if we have questions. I assume we have time for questions.
Absolutely. Dr. Benford, this was phenomenal. We all have goosebumps here in the room. I'm going to pass the microphone to Bill.
Hello, my name is Bill Spizzeri. Great presentation, extremely detailed, very interesting. Thank you. The Roman is going to be in space, large field of view. Recently, the Vera Rubin Observatory land-based large field of view came online, I think about a year ago or something like that. Can you just generally compare the two of them? Also, if I can ask a second question, I didn't hear when Roman is going to be in space.
Sure.
Thank you.
So I'll answer the second one first. So what I had said earlier is that when we began in earnest in the construction phases of this observatory, we had committed to launching it by May of 2027. We anticipate it will launch in fall of 2026. The launch date is something that is not entirely in our control. We're launching from Cape Canaveral, from the Kennedy Space Center, on a Falcon Heavy, and the queue of those is limited, so we have to wait our turn, in essence. So we expect it'll be sometime in the early fall, and it'll of course be broadcast like all of our launches are, and you'll hear about it. In fact, I would say we will probably know within a few months when the launch date is, when the queue for the Falcon Heavies is determined. So watch for that. Now, the other question is one that I really should have touched on, but since I work for NASA, I tend to focus on our NASA missions. The Vera Rubin telescope, which is conducting a similar wide field survey of the sky in visible wavelengths, had its first light last year and will begin its survey operations sometime in the very near future, I believe. Now, it was designed for some of the same kinds of observations that Roman was designed for, to conduct wide field surveys and measure galaxies and measure the distribution of matter in the universe. It does this in the visible, and it does this from the ground. So even though it has a much larger telescope, it ends up having roughly the same sensitivity as our smaller space-based telescope. Unfortunately, it does not have quite the sharpness of view that you get from space, but it does have a wider field of view. It has a roughly 3 gigapixel camera, if memory serves, I didn't mention this, but the Roman infrared camera is 300 megapixels. It's the largest infrared camera, to my knowledge, that humanity has ever built. So Roman has a very precise camera, one with very sharp, crystal clear vision. It's designed to be very, very stable, both in terms of its point spread function and its photometry. And so you can measure the shapes and brightnesses of objects with an accuracy and a precision that has never before been possible. Since you're all astronomers, you would appreciate things like this, that we can measure the relative brightness of objects that are, I think, 12 magnitudes difference to a fraction of a percent. And we can measure the shapes of objects stable to a tiny fraction of a percent, and the locations and positions of things to tiny fractions of a percent. So we can usher in an era of precision astronomy and astrometry and photometry that has never been possible before. Rubin will have more sources, more observations, and more data because it's a much bigger camera and it's repeatedly imaging the same sky, but it don't have the same level of precision. Now you can combine those two data sets and you can get the advantages of both. And we've designed the two missions, the two projects, with that very much in mind. Roman does not have as much capability in the visible. It does have a visible filter that's roughly an orange filter, if you think in actual visual terms. It's sort of short, slightly bluer than R band. Rubin has a set of filters in the visible, which combined with Roman give you a much broader panchromatic kind of view of the visible and near infrared. We designed them on purpose that way, so that Roman's filters and Rubin's filters work well together. We're planning on observing many of the same fields. Rubin can only observe in the southern hemisphere because it's located in Chile. Roman can observe anywhere, but we're placing most of our high latitude survey in the southern region so that it overlaps with Rubin, so you can do these combinations that I mentioned. I hope that addresses your question.
Yeah, yeah. Don?
I understood you're going to have about 20 petabytes of data
Yes.
in the first 5 years of the mission. I can only imagine, since they're going to be in the cloud, that you're developing some AI agents in order to be able to manage and then also analyze some of that data. Could you make a couple of comments on what may be going on there?
Certainly, it's a great question. Yes, the data will all exist in the cloud, and it's all very accessible, and you can do deterministic data processing for many things that you can imagine. But you won't be able to do visual inspections and object identification yourself. You'd have to figure out how to have a computer help that, even if you didn't have AI, because there's no time for a human to individually identify and classify 100 million galaxies, or even an army of people, realistically. So we are focusing a lot on the development of tools to help that and to run those tools natively in a cloud-based environment where you can bring your code, written in Python or whatever, to an environment where it processes there with the data. We're focusing on predominantly the subset of artificial intelligence that's known as machine learning, which is different from the large language models and the generative AI that you hear so much about in the media, because that's really cutting edge stuff. We don't need as much of that kind of focus, but we do need the ability for machine learning, where we train the models on the data that we have and then allow it to make discoveries on the data that it's then shown. We've been doing this quite a bit actually already. Some of the reason, in fact, a fairly significant reason why we have the high fidelity image simulations that I showed you earlier is to begin training a lot of those models. We had to build them so that we could understand exactly how to do our data processing anyway, but part of it is that you can then take these things that we've built where we know what the galaxies are like and we know what they look like, and give them to an AI tool where the machine learning is trained on a subset and then it predicts everything else. And we know what's in there, so it gives us truth, and we can then study how well we can make that happen. We have several groups at universities around the country who are working on this kind of work actively in preparation for the time when all that data starts to flow in, because we're not going to have enough time to learn on it while the data are pouring in before we might end up getting to the point where it becomes challenging to keep up. One of the issues that we recognized about Roman a couple of years ago is that if you start doing the processing and you process it for some length of time and discover that there's some major things that mean that you have to go back and start reprocessing the data from the beginning. While we're still taking data, we can only do that a couple of times for maybe the first 2 years or so before we get to the point where if we go back to the very beginning and have to reprocess everything, that we may actually not ever quite catch up, in the sense that we will be taking data so fast that we won't be able to get through all of the data to get back to it. So we're very cognizant that we have to make sure that our data processing works very well from the beginning so that we can stay current. It's not quite as dire as I made it sound just then, because we will eventually get it all done. And the elasticity of cloud-based computing means that you probably can actually make it catch up. Computing will get better. But it is a concern that you can't let yourself get behind when you're adding a terabyte a day, and you might have to go back and look at it again. It was a bit of a rambling answer to the question, but I hope I got it.
Incredible.
I appreciate it very much. I mean, I just from having done a little bit in Galaxy Zoo as a citizen science project, I mean, I'm just blown away by that. Thank you.
Well, thank you for your service to citizen science. We have a couple of projects for Roman that are already underway to prepare for citizen science with Roman for very similar purposes, because when I mentioned training, part of what we need is something that looks like truth to train the computers on, and citizens doing citizen science on galaxy identification, for instance, is one of those things where a human is probably the best arbiter of truth that we have. So thank you.
Wow, great. We're looking forward to do that, right, Don? Absolutely. More questions? Maybe a little bit further in the room? Oh, one online. All right. Yeah, I'll give some mic to you, Mike.
Trent asks, what specific data are we hoping to gather from the telescope that will increase our knowledge of dark matter and dark energy?
Okay, so this is a broad question. What data do we get? So since you're all astronomers, fundamentally the data we take are all digital data in, approximately speaking, two-dimensional imagery. If you're familiar with FITS files, we don't use FITS files anymore. They're now ASDF files, which are slightly more advanced. And we take data with most of our Roman data is taken with a wide field camera that has an element wheel, not just a filter wheel, but an element wheel that allows us to rotate between 11 different positions, one of which is a dark filter, essentially a blank off that has calibration standards on it. The others of which are predominantly various bandpass filters ranging from essentially something a little bit bluer than R band going out to something a little bit shorter than K band, or roughly 2.2 microns in the near infrared. There are also two dispersive elements. There's a prism and there's a grism that provide slitless spectroscopy. So every star or every galaxy is spread out into a spectrum, a short spectrum, a few hundred pixels long. And all of that imagery data can then be processed. It's a rather difficult process that requires the data be taken in various ways, different roll angles, so that you can separate things out, and can be reassembled into a data cube in the case of the spectroscopy ones, or a data stack in case of the multiple band imaging ones. So fundamentally, those are the data products that we provide. How you infer dark matter and dark energy, this is a really interesting one. There are a variety of ways to do this. One of the ways to trace dark energy is from the brightness of supernovae, and we could do an entire talk just on this because that was the subject of the Nobel Prize for the discovery of dark matter was based on supernovae. So what you would be looking at is changes in brightness of supernovae over time and measuring the distances or the redshift to those supernovae to use them as a standard candle for the distance of the universe and therefore the expansion history. We would also, by using the spectroscopy of galaxies, be able to place galaxies in three-dimensional space very precisely, and to use that as a standard ruler for the expansion history of the universe based on, this is called baryon acoustic oscillations. It's basically the leftover sound waves from the Big Bang that have a certain angular scale where it is most likely to see galaxies at a certain separation and to trace that across time. Similarly, we can also use that kind of data to trace the existence of cosmic voids. So voids are actually the largest structures in our universe, not just the clusters of galaxies, but the space between them. And the space between them is a result of the dark matter that collapses matter, but also the dark energy that pushes space apart. We can measure those using similar data. And then weak lensing, which is like strong gravitational lensing, but it's just a much, much smaller signal, So for every galaxy you look at, there's some distortion from the intervening mass of all the dark matter and galaxies between that object and you. And by measuring hundreds of millions of galaxies and getting their shapes very precisely measured, we can map out the three-dimensional structure. And in the little image that I've got on the screen right now, the sort of bubbly stuff that you see behind that, it's, if you will, a little bit like the foam of the universe. And that clumpiness of dark matter is something that we can measure by this precise shape measurements. There are a few other techniques I could go into with dark matter and dark energy, but those are the biggest ones that are the most important for us. And gosh, each one of those, people can give you talks on just that method.
Absolutely. Did that answer the question, Mike? Yeah. Yeah. Are there more questions from online? No? Any more questions in the room? No? No? Spectroscopy question. There's a GRISM there. Yeah. Well, yeah. So it's yeah, maybe you can talk to that.
We have a GRISM aficionado in the room.
Yeah. We have a couple of spectroscopy builders in the room, and
Okay.
so maybe you can talk about the GRISM and how that would work, and
Sure.
telescope, yeah.
So the two dispersers we have, there's a prism and a GRISM. The prism, of course, is actually a multi-prism. That one is designed primarily for doing spectroscopy for the supernovae. It's a low resolution, R of about 100 if memory serves, and it covers a very broad band, and that is used for doing spectroscopy of supernovae and the galaxies in which those supernovae exist, the host galaxies. We don't need a very high spectral resolution because really what we're looking for in the case of supernovae is to get the redshift of the supernova, and there are features like the silicon absorption feature, which with an R of 100 you can easily pick out, and you can trace the redshift quite easily out to a Z of about 1.7, if that's a familiar term. So it's light that's more than halfway across the history of the universe. The GRISM is a resolving power that varies with wavelength, but is more like 500 or 600, and it covers a fraction of almost an octave in the near infrared, and is designed for the spectroscopy of galaxies in order to make those three-dimensional maps of the galaxies in the universe, predominantly by looking for the redshifted H alpha line, which is approximately 0.6 microns, or roughly red light. But by the time you get to a redshift of about a half or so has shifted into the near infrared into our GRISM's band. So between a redshift of a half and a redshift of something like 3 is where will be able to make precision measurements of the redshifts and distances to those galaxies. For those of you who are familiar with space telescopes, there was one launched recently called Euclid, which was an ESA-led mission. The European Space Agency designed and built Euclid to do many of the same projects that Roman is doing. It'll do weak lensing mapping. It'll do this kind of galaxy spectroscopy. It also carries a set of GRISMs. I can't remember how many it has, 2 or 3, to do a very similar kind of work. But it's a smaller telescope and slightly different wavelength range. So it'll be an interesting thing to compare all of our results with these. But yes, there are quite a few of these slitless imaging systems coming online now. Of course, Hubble has this. It's a bit of a specialty instrument. Not many people use these. The GRISMs on most instruments. Much harder data to process.
Yeah, we in the amateur spectroscopy world, it's a technique that we use as well.
Yeah. It's very powerful, but it's a lot more processing intensive.
Yeah, absolutely. Good. No more questions, no more online? No? Well, Dr. Benford, thank you so much for this inspiring talk. It was amazing. So, yeah.
Okay.
So
thank you all so much for having me.